All right, ladies and gentlemen, welcome to part 3 of your concept map video dealing with rotational motion. I want you to pause on this video and try this question out. If not, I'm going to I would say, in-depth walk through this question on how to do it. Alrighty, so let's go ahead and get started. So the first thing I'm going to do is talk about how to draw your free body diagrams when you're talking about beams. And so the first thing you want to do is look at your center of mass. So if we're looking at this beam, the center of mass is going to be halfway right there. And what is that force pulling it downwards? Well, you can say force due to gravity, or you can say weight. That's it. That's all done on the free body diagram for this one. So for there, we can start to solve this problem. So in A part 1, we get net torque is something that they want us to simplify for and solve. Well, the only thing causing this beam to rotate would then be its weight. So that's the torque from weight. To calculate torque, then you would have to say this also equals, force. If we remember, torque equals Fr sine theta. We can then say that the force is going to be weight. The radius here, if this whole beam is a length of L, how long is it from, let me erase that real quick. There we go. How long is it from here to the halfway point? Well, that's just going to be L divided by 2. Weight can be broken into mass times gravity. L all over 2 equals torque net. And that's it. So moving on to part 2, how then do we then find our angular acceleration? Well, if we remember, torque net also equals I alpha, and that I value is given, we're going to then say torque net, which is I alpha, equals mgl all over 2. This I value is given. You're never expected to memorize them. They're always going to be given, or you're going to be solving for them. And so when I write ml squared all over 3, you will be given that. We got mgl over 2. So what we're going to do here now is cancel out some of our units that we don't need. Mass is gone. Length cancels out on one side. So we can solve for the angular acceleration of this system is going to be 3g all over 2l. Okay, moving on. The linear acceleration experienced at the end of the beam. Now, if we remember, when I told you about linear kinematics, you can take any angular component and take its linear component and divide it by radius. So we're going to take angular acceleration equals linear acceleration all over r, and so what we're going to do is plug this right on over here. So angular acceleration is 3g all over 2l. We're looking for that angular acceleration at the end of the beam. So what are we going to use for our radius? Well, how long is the beam? Or how long is it from the rotation? And so that's just going to be the entire length, L. So just like we did before, let's cancel out some units. Length disappears, so the acceleration at the end of the beam is 3 over 2g. All right. That part, or part 1, is, or part A. Part 1, 2, and 3 are done. Now look at the linear acceleration at the hinge. So I'm going to go right on back to saying this. If we're looking at the hinge, how far is the hinge away from the hinge? 0? Well, yeah. So what's your linear acceleration then? Well, linear acceleration should also equal 0. That's it. Since there is no net torque, or there can be no net torque, there can't be any linear acceleration because itself is not moving. All right, and then part B is determine the point where linear acceleration will equal g. And I'm going to go right on back to what we just did. So what we have is angular acceleration equals linear acceleration over r. Now, angular acceleration, we just denoted as 3g over 2l, so it's 3g over 2l. The linear acceleration we're shooting for is one is it equal gravity, and the radius from the center is what we're looking for. So all we're going to do here now is solve. We notice that something disappears, gravity disappears, and we get the radius then equals 2/3 of your length. So there's a couple of interesting things we want to denote there. Is if we got my beam right here, what was its angular acceleration throughout the whole thing? Well, the angular acceleration was constant. It didn't rotate. When it did rotate, it did not change its acceleration while it rotated, its angular acceleration. Its linear acceleration, though, we noticed as it increases, as your radius increases. And how do we see that? Well, here at the hinge, it was 0. At the all the way at the far end, it was 3/2 g. And then at the 2/3 point, so if we got that half, here's about 2/3. So the linear acceleration here is going to be equal to g. So the further out you go, the faster that point on the meter stick is going to accelerate. Now, there's a couple of cool, I would say, experiments that show this. You can kind of Google those and look for them on your own, but we're going to leave it here. I'm going to kind of dive into the next topic is, what if we take a meter stick and then we look at momentum? So if we look at linear momentum, remember linear momentum is mass times velocity r, or you can say it's linear momentum times radius. It's been a little while since we talked about this, so make sure this is kind of tucked in your back pocket. Now, from here, we then can solve this problem. So I'm going to pause the video, try to solve it on your own, and then go from there. But I'm going to go ahead and get started. So the first thing we're going to denote is that this is a collision. So we can then say the angular momentum before equals angular momentum afterwards. There's only one object moving before the collision, right when this ball hits the end. So we're going to say that the angular momentum of the ball right before the collision equals the angular momentum of the rod after the collision plus the angular momentum of the ball after the collision. You could say that, you got angular momentum of the rod before, but it's not moving, so this comes out to 0. Alrighty, so I'm just going to move forward from here. I'm going to go ahead and solve for angular momentum of the rod. That's of after the collision is going to equal ball before, ball afterwards minus, of the ball before. Now, remember when you do momentum questions, you have to keep in mind your direction. So let's expand these a little bit. So I'm not going to use this anymore because we're already good here. So angular momentum of the ball is going to be its linear momentum after the collision. So we're just going to call that final times your distance of the rod, or your radius, so that's going to be d, minus momentum initial times distance. However, I just told you to remind yourself about direction. What direction is your initial momentum? Positive. What direction is your final momentum? Negative. And so what we get here is, negative PF D minus P initial D, and then bringing ball afterwards over here, we then say negative L ball afterwards. You notice all my negatives disappear. I guess there was a way to do this a little more simply and straightforward, but now we notice that we can factor out a distance here. So we got P final minus or plus P initial times d. Alrighty, guys, that is a tricky problem. Kind of looking at the direction of things and reminding yourself when you're looking at momentum, you have to be careful of your directions. So we're looking at the answer of D here. Alrighty, the last video on this concept map chunk will look at in depth on angular momentum of a beam and looking at an FRQ specifically. But for now, we're going to call that a wraps, and I will see you on the next video.